I am Julian Samaroo. I am a research software engineer at MIT's Julia Lab. I do not live here in Boston. I actually live in Tennessee, but that's beside the point. For the purposes of this talk, you can know me as the maintainer of Dagger.jl. What is Dagger.jl? So Dagger is, from a high level, it's a parallel computing library. So it, like many other libraries in Julia, it allows you to do parallel programming, multi-threading, distributed computing, GPU programming. All of that's possible with Dagger. All of that's wrapped up through various APIs and interfaces in Dagger. For the purpose of data processing, though, because this is the data mini symposium, Dagger basically has a concept of data locality. So, there's many libraries out there like, that you'll see in Python and such that kind of don't really pay attention to the different places that data can be. They don't really have a concept for, hey, maybe my data is not here locally in memory, maybe it's on a different process. And I still want to be able to work with that data. And it may only have, other libraries may only have the concept of there's one data type or there's a limited number of data types that, you can work with. And Dagger does not limit you to that. Dagger has, internally knows about types of data, where data is. Is it on another process? Is it in memory? Is it on disk? What is disk? Could it be a database? Very flexible, has a lot of internal machinery for kind of handling all the different places where your data can be. And it so anyway, I'll show some more of these details as we kind of get into it. But the purpose of the talk today is not to focus on Dagger itself, but to focus on a library which uses Dagger called DTables.jl. What is, basically, why do we need another table implementation? We have data frames. Data frames is amazing, as we just saw, as we probably already know. So why do you need another table library? Well, really, it's for this model of data locality and really being able to extend the data model into different modalities and to different hardware. So what DTables really is it's basically taking data frames or other table types and merging their functionality together with Dagger. And what that lets you do, so you can use DTables with data frames, works excellently. But what it lets you do is do things like distributed computing with data frames, which normally you cannot do. You can, but you have a lot of manual work to do to kind of make that happen. With DTables, that's built in, that's automatic, that's the default model, you don't even have to think about it. And of course, this extends to other table types as well. You can work with data that's on disk, Arrow files, CSV files, SQLite databases. Really, the list is endless. There's no restrictions. Something I'm going to show a little bit today that we also enable is out-of-course support. So, it's great to work with an in-memory representation when your data fits in memory. What happens when it doesn't? What do you do when your data is simply too big, or you're working with these files that just contain historical data from so far back that there's no hope to ever fit it in memory. You really can only operate on it piece by piece at a time. And DTables enables this. And this is what I call out-of-course support. And so we have this built in. Again, this is basically automatic. You call, there's one function call, and then it turns on out-of-course support, and that's it. And then everything just seamlessly does out-of-course. And I'm going to show this in just a second, so let's actually take a look at that now. So here I'm just generating some data. That's just a little helper for me. So let's actually construct a DTable. So what we're basically doing here, this is kind of a lot of stuff, but we basically have a bunch of Arrow files on disk that in sum, it's like 20 gigabytes of data across all of these files. They're just very simple tables. They have 2 columns. Doesn't really matter. But basically what we're going to do is we're going to use Dagger to lazily reference all of these files. So this Dagger.file function here is basically saying, okay, give me the path to your file. Tell me how to read and write it. So arrow.write and arrow.table. Those are your serialization and deserialization functions. With those, you can go between in-memory to on-disk and back. And don't mind the use IO equals true. That's just kind of a separate detail. Basically, what we're doing here, though, is we're constructing this vector of all of these files. They've not been read in yet. We haven't even checked that the paths exist. But what we're doing is we're creating this DTable from these lazy references to these files so that we can then work on data which is bigger than RAM. I mean, on this laptop, it's probably fine, but I worked on this code on a laptop that only has 16 gigabytes of memory. I had 20 gigabytes on disk, and I was still working on it just fine. And the DTable enables that through a mechanism like this, where you just basically say, here are my files, don't load them into memory. I'm gonna tell you what to do in a little bit, but like, just give me a table object that I can work with. So we can see that when we actually create one of these, we get, it just prints out, okay, it's a DTable with 172 partitions. What does that mean? So the way that the DTable works under the hood is that it takes your greater table, whatever your table is, whether you already have one in memory or whether it's spread across a bunch of files on disk. And it basically says, okay, we're gonna partition this data. We're gonna split this into separate subtables, and that is gonna be kind of our currency, the lowest layer. We have a bunch of these little subtables, and they're basically, you can imagine they're just stacked on top of each other. So each partition is just a set of rows on top of or below another set of rows. That's it. And so if I was to actually run this, I'm not going to do a real-time running of code because we all know how that goes. But if you run this, it's basically immediate. Doesn't matter how many files you have. Constructing this partitioned DTable takes almost no time at all. And it's because it's lazy and it's partitioned, we just basically have to see there's a bunch of files and that's it. So anyway, so I kind of went over some of this already. So I'm not gonna show a whole lot of operations, but the point I'm gonna make here is that you can basically the intention is to be able to do all the same operations that data frames exposes, the DTable strives to support. Obviously, that's not currently the case that we have support for all of them, but we would love help to implement all of these. We have to keep up with data frame's amazing pace of development, so, but we'll, for example, so, okay. What we have here is, so we constructed that table above, right? So we have this big table, it's 20 gigabytes, whatever. And we want to operate on it, but again, we only have 16 gigabytes of memory, no problem. You can run regular functions on this DTable, and it is going to work just fine. And the reason for that is that under the hood, the DTable is essentially breaking this operation down into a set of smaller operations on just those partitions that we have. It's saying, okay, give me the first 2 partitions. Let's do a reduction on those. Then the next set of partitions, we'll do a reduction on those. And then at the end, we're gonna combine all of these with a single final reduction or something along those lines. Now, of course, all of this happens multi-threaded, distributed, in parallel. You don't have to ask for that. That's built in. That's kind of just part of the model. So this can be really great. You have a lot of files, but you also have a lot of Julia processes. You can start a lot of workers. Maybe you have a local cluster that has a ton of workers. DTable will make use of all of them. It's going to just split those partitions across all of your workers and just start working in parallel, start using multi-threading automatically. So let's actually just quickly look inside the DTable. So as I said, there's basically partitions or chunks. You can call them either. I tend to refer to them with one or the other. Each of these partitions or chunks can be any table type. It could be a data frame, arrow.table, whatever. Could even be heterogeneous. I do not have an example of this today, but we strive to support the sort of case where, say, your organization has a bunch of historical data that was in CSV, and then at a certain point they decided to switch to Arrow because CSV files are maybe not the greatest long-term storage format, and so that shouldn't be a problem at all. You can load those in just fine, and if that does not work, file an issue and we will fix it. But the point is, each partition is its own little table, any type, no problem. And so if we were to actually look at one of these partitions, we call them chunks in DTables, we see, okay, it's just an arrow.table. Really simple. It could have been a data frame, it could have been a CSV file, whatever. So now you actually see that I use this, that I'm calling fetch here. So one important concept when you start working with anything that uses Dagger is that things are asynchronous, things are lazy, things are happening in the background. They're not, you don't run a command and sit there waiting. You run a command and you go and execute the next command and the next command, and you keep going, batching up all of your work, and in the background, Dagger is dispatching all of that work, sending it off to workers, moving data around. You don't even see it. It's happening in the background for you. When it comes time that you actually want to materialize that result and be like, okay, I'm ready to stop and see what I actually have here. Like, show me the results, you call fetch. And you can do this on basically any operation. They're basically all lazy, so you can just assume that you can call fetch on the result of any operation and physically materialize something. Now, I'm not going to do that because obviously 20 gigabytes versus 16 gigabytes, I don't want to kill my Jupyter kernel. So, but we'll just take we have just one partition here. We can do that just fine. It's 100 megabytes or so. And here, we're just kind of showing that in this specific table, it's homogeneous. It's just arrow.tables, but there's no reason that that has to be the case. You could have other table types, no problem. And again, don't load 20 gigabytes into 16 gigabytes of RAM. It's not going to work. Now, caveat. This support there is an amazing storage system behind Dagger that makes all of this work, but it's a lot of work to get out of core working in a language like Julia where we have a GC, because we can't always guarantee that, well, we know that the memory has been freed. We know that we have enough space. And we can go ahead and load more stuff from disk. We don't always know that, so sometimes if you use the DTable, you might run out of memory when you expected that it would, basically that you wouldn't. This is a thing that we're working on fixing, but all of the infrastructure for managing the swapping of data from memory to disk and back and forth to satisfy the operations you need, it's all there. Mostly just figuring out Julia's GC and getting it to cooperate with us. And if you're going to be doing out of core, Arrow works excellently for this. CSV, because of all of the parsing and allocations that have to be made, does not work as well. So maybe just keep that in mind for the short term. So for the rest of this talk, I'm going to just basically show how we work with a smaller DTable, just to kind of see what we can do. Same invocation as above, except this time I'm only loading 2 of my partitions into this DTable, and we see that down here, DTable with 2 partitions. Now, I know that this is printing out a table type of data frame here. I'm going to show you what that is in just a second. This is an important point, but let's just hold that for a moment. So we can see that data frames operations work fine. You can use select. You can use quite a bit of the data frames mini language. The goal is to support the entire thing as much as is possible. We basically want users to be able to go from data frames to DTables, no problem, seamless transition. So we strive to support that API as well as the Tables.jl API, which is a little bit more compact. So both of them, of course, give us a lot of capabilities, which we'll see in just a second. So we can go ahead, we can do our operations, no problem. This map operation, as I said before, it's happening in the background, it's lazy, and then at some point we're like, okay, let's fetch this, let's take a look at this. Okay, so we multiplied this column by 2. Great, really simple. Now if we actually take a look at the output of one of these operations, so this is looking at table 2, which is this one right here. And if we look at the partitions, the chunks that this D table contains, we went from an input table of having a bunch of arrow.tables to now having a data frame. And this is not a forced conversion. This is, you don't have to just go to data frames. You can go to other table types. You can keep working with arrow tables. You can use a name tuple of vectors. You can use really whatever table type you want. As you transition from operation to operation, you can basically say, hey, I want you to go to this table type. Change to this for whatever reason. Maybe a certain operation you want to do is more performant with a different table type, or maybe you're going to be writing it out to a file. So you have control and flexibility there. Now, of course, this table is smaller. I just took 2 little partitions. We're able to load that into memory just fine. If you want to just materialize a D table and you know it's going to be fine and it's not going to blow up, you can just use standard piping syntax and materialize a data frame, no problem. Joins work as well. Christian, who is the one who actually maintains DTables, has put a lot of work into getting joins working really well, working really efficiently, and using resources as much as possible, using multi-threading, distributed computing, and just exploiting as much parallelism as possible. So joins work well. You can join between a data frame and a D table, no problem. I pulled out one example where we joined onto D tables because of the aforementioned out-of-core GC issues, but the functionality works. And will certainly be improved in the future. There's a lot of effort going into getting our out-of-core support very robust, so expect to see a lot of developments there in the next few weeks. Now let's look at, so I kind of mentioned heterogeneous support. So basically, what does this mean for you? Usually, a lot of the people here are not just working with stuff that you construct in memory. You're reading from files, you're writing to files, you're working with things that already exist on disk, and you're just kind of doing operations on that, and often it's just kind of load data, process it, write it out, and go on to the next step. And this is no problem with the D table. So basically, what I'm going to show here, what I'm showing right here is, okay, we're taking a table and we're writing it out into a bunch of different formats. So it's starting off as a data frame, doesn't really matter right now, but we're writing this out to Arrow, to CSV, Parquet, SQLite, and Julia's built-in serialization format. And what we're going to do is just round trip them, just to show that we can basically read in any of these formats that are Tables.jl compatible without any problem. It really doesn't matter, because the D table is agnostic to where your data lives, but it's aware of it when it needs to. When it needs to go and actually read it. It knows how to process it. So here I'm just basically saying, okay, well, for an arrow file, use arrow write and arrow.table, for a CSV, et cetera, et cetera. A lot of this we also hope to automate soon. Basically just look at the extension and figure out, okay, what package do we need? Kind of like file IO if you've used that. And we can read these into a D table lazily, just fine. It's all the same no matter which format you're working with. So this is really convenient. It also goes the other way. I didn't get a chance to put in the writing aspect, but there's also going to be a Dagger.to file, which kind of looks like, it's kind of like how we have arrow.table for reading, arrow.write for writing. And the D table basically has Dagger.file for reading and Dagger.toFile for writing. So that'll be out there soon in the next few days. But you can assume that you can read in from a file, do your processing, and write back out into whatever format you want with the D table, no problem. So from backing up from tables for just a second, what kind of formats can you work with? So tables obviously are something that we're all familiar with. I'm sure most of you probably are working primarily with tables, but there are other formats out there. Tables are not the only thing. And so you can work with other objects as well. If you want to work with arrays in the same sort of manner, lazy, asynchronous, distributed, multi-threaded, parallel, reading stuff from disk, writing stuff from disk, Dagger's D-array does the exact same thing, not because we implemented all of that functionality a second time for arrays, but because we only have a single underlying storage engine that works for really any abstraction that you want to build on top of it. Tables, arrays, arbitrary data where you kind of don't have a table or an array, but you really just have an object that you want to work with, which might be on disk or in memory. I already showed you Dagger.file for kind of working with a lot of this. We're also very open to other formats. Distributed graphs, for example, if you're doing graph theory work or machine learning on graphs, that's something that we want to support. And really anything you can come up with. If there's a format or modality that's missing, file an issue, we can talk about it. And you can build right on top of this storage engine, no problem, and get all of these benefits that I've shown with a minimum amount of work. So real quick, I'm gonna just kind of show what this looks like, because there's a lot of details under the hood that I haven't really shown you. So Dagger has these, Dagger's unit of data is called a chunk. And what a chunk basically is, it's a lot of things, but for the purpose of this discussion, a chunk is basically just a reference to some data with some type that lives somewhere. It might be in memory, it might be on this worker, it might be on another Julia worker. Doesn't really matter. It's all handled by chunk. And a chunk is basically something that you can pass around freely and within the Dagger ecosystem, and things kind of understand what that is. So I am out of time, so anyway, that's great. Powerful and extensible. We support all of these modalities, distributed, multi-threading support. Yeah, basically, we're looking for contributors as well to help us develop more of this, to cover more of the amazing development pace of data frames. All of these fun things coming up soon in the future. So thank you very much. Thank you.
So,
if we have
questions, so yes, I was wondering if there was the assumption that all the files, the partition of files, are treated independently or by row. For example, if there's, for example, a lag operator or a group by that overlaps different arrow files, would that still work? So are they like combined together, or they have to be treated as completely independent entities by Dagger?
Would you mind rephrasing that just slightly? I'm just tying the concepts together.
Yeah, I'm wondering if the parallelization that happens if there are, let's say, 2 arrow files, is it the assumption that all the operation will happen fully independently, let's say embarrassingly parallel
No.
fashion, or if there's, for example, there's a group by that concerns an overlap over the data that are part of the 2 files, it will still work?
Yeah. So Dagger is fully aware of the possibility that your data may be in different places, and you need to work across kind of things that may be in different locations, in different formats, but it will also recognize things are in the same location, so do the most optimal, the fastest thing. You basically, under the hood, when you define how a D-table works, those details are presented to Dagger in a way where it kind of understands that locality, and it sees whether your operation is embarrassingly parallel or whether it's like a reduction, it's spanning a lot of different objects. So that's under the hood, kind of in the API, the interface with Dagger. hopefully that answers your question.
Yeah, thank you.
Thank you.
Okay.
Yeah, maybe just maybe a bit of a naive question, but with lazy loading, you mean like, for example, if I'm reading a file, a really, really big file, and I want to filter observations not after I loaded it, but as I load it, is that what you mean by that?
So to an extent, no. Basically, the first thing I'd say if you have one of those situations is if you can split that file into multiple pieces before working with this, you're going to get the most mileage. And mostly that just comes down to the fact that we don't really integrate directly into the table packages and kind of make them start working in like this partitioned approach, but more that we already have partitions to work with, that the user kind of gives us those partitions in some format. Of course, if you pass in a big data frame, you can tell the DTable, hey, split this up into partitions. But if you're talking about files, if you want to be able to do what you're doing, it would be best to have your file split into multiple. And we could see what that would look like in the future to kind of have some kind of streaming operation framework, but it's not currently a thing that we have. Great question.
So like maybe let me add a short comment. So the requirement is that the file reader must be able to provide chunks.
Yep.
And for example, CSV provides chunks, so then it would not be a problem. But if a file reader would have to read the file as a whole, then there could be a problem.
Exactly.
Yeah, and the last question?
It was very much
Okay.
a question because Arrow and now the data frames supporting the iterator and Arrow basically allowing you to read all the different chunks in chain vector.
Right.
I was curious if you can leverage those different chunks to make different pieces of work, your chunks.
My understanding of this, and you'll have to ask Christian for more details about this, but my understanding is that yes, we support that. Through the tables.jl interface, there is essentially a partitioning mechanism, and we use that to determine, hey, do we have partitions here that we can use? So yes, that should work. So it kind of a yes to your question sometimes. It depends, so yeah.
Okay. Okay, last one question.
Maybe you already discussed about it, and I missed. So when we are doing the partition, the chunks get assigned to different, like chunk 1 or chunk 2. Like on what pieces is the partition going to happen? Like is it like a random sample of the data set, or just like 1,000 top 1,000 rows in chunk 1?
So just to kind of rephrase, when you're working with say a large piece of data and you're partitioning it, how are the partitions laid out? They're just a linear, basically DTables will pick a chunk size. You'll say this is how many rows should be in each partition, and then it's just gonna linearly go through and slice out a partition from the input table, and they're just laid out basically linearly. Yes, yes. Especially if you already have another table, you can pass it into the DTable constructor, and the second argument is the chunk size.
So again, one short comment. So if you work with databases, it is the same. You have to think about skew exactly like you have to think about it when you're designing a database. That kind of user has control of it, but DTable won't guess for you what is the layout of your data.
Right.
Okay, so thank you very much.
Thank you.